I'm Gabriel. I'm a PhD at Imperial College London and part-time researcher with SpinCloud. And thanks to Tom, we've got a nice introduction to training network with input. And I'm going to be giving somewhat complementary talk on now actually deploying this training algorithm on chip on the Spinnaker 2 machines. So a little bit of context. Why would we want to train networks on chip? There's different reasons. Seeing the hungrier nature in energy of current AI, we kind of want to reduce this energy footprint during training. It could also be a key for unlocking good potential of embedded agents during training, having agents that adapt or on the edge devices. And for all of this, we need algorithms that actually retain the sparsity of event-based communications during training as well, right? Another point that I think is interesting is we also might want to use exact gradients. A lot of amazing work has been done with surrogate gradients, and these has been incredibly effective in training SNNs in the past years. And it's been suggested that actually surrogate gradients are a way to robustify our networks, but the impact of using surrogate versus exact gradients is still not fully understood, in my opinion. The key to all of this is that on-chip training is actually fairly hard, right? I'm going to go briefly over the event prop algorithm since we've been talking about it a lot, but basically this is a purely event-based, which is very good for all hardware and aligned very well. And this means we still conserve sparse sampling in time. And the idea is that we can basically run the SNN forward in time and then run the simulation backward in time with a different set of dynamic and use these new activity to recover exact gradients. So this is not much more expensive than running a forward pass, right? In terms of the data set, we use the data set from this yin, which is small scale, so easy to fit on chip and not linearly separable, meaning shallow networks still somewhat struggle to learn this. So this helps us validate the fact that gradient does propagate in multi-layered network, right? Going a little bit fast over these details to have more time later. This I'm going to spend a bit more time on, right? So this is how did we actually implement this on chip? So our, let's say, general event prop training is composed of 4 programs, right? You can see the input spikes. They're going to input some data input spikes into the network. We've got 2 neuronal layers, right? They're going to process the forward and backward pass. And then we have also a separate loss computation program. These 4 things will constitute one batch that is able to process one batch or one sample at a time, right? The Spinnaker 2 chip is composed of these 152 parallel processing elements. And the way we map it to be able to have batch parallelized processing is that one of these 4 programs are going to be mapped into what we call one quad PE. So these are 4 processing elements that sit locally on a chip. This is quite nice because that means that during the processing of one sample, these PEs can only communicate locally to each other, reducing overhead, right? In addition to this, you need a global optimizer and a global, what we call kind of command central. And this is one processing element for the entire chip, and this implements Adam and has different roles. It has the role of a synchronizing sample processing, gathering gradients once the processing is done across all the other processing elements, computing new weights, implementing the Adam algorithm optional weight decay, and then dispatching these new weights via the network on chip before actually starting the new sample process, right? There's also a little bit of details on the exact structure on how the host and the chip interact, but I'm not going to get into this too much. Basically, there's a high-level Python experiment runner when we can define the network and relevant quantities that then interact with a lower-level experiment runner in C++ that then interacts with the chip. What we developed doing this work is also a fully identical off-chip simulator, and that was very useful for a few reasons. An off-chip simulator allows you to do efficient prototyping and debugging, right? If we know the dynamics are completely the same, then it's always a bit easier to have something running locally on your laptop or GPU. It also allows you to do efficient parameter search and optimization. So these simulators that are developed is a custom PyTorch package. It completely matches the on-chip behavior and is available open source. That also allowed me to do hyperparameter optimization completely off chip, right? So I used a software package with biases to do Bayesian hyperparameter optimization to get the results that you're about to see. Something I'm really excited about having these off-chip and on-chip implementation completely matched is the ability to do some hybrid training, which I'll talk about it a little bit later. On the right, you can see some examples of some voltage and current traces, and the difference is minimal. Differences in gradients computed are also very small. Some results. We trained the network in 2 regimes. One that would call the full data set, which is 5,000 training sample with batch parallelized processing and 20 epoch, and we get some pretty good accuracy out of this. We can see the on-chip and off-chip get very close results. And there was another regime which I call somewhat an online regime, where we actually only see 300 samples one at a time, a single path through the data, right? And this was interesting to me to kind of start thinking about more online or continual approaches, even if in this very simple setup. So this demonstrates the viability on training on chip, and we have also some energy profiling results. Please do take these with a grain of salt, because I did this a bit crudely. But we can see that basically for a forward plus backward plus 1 time step for update. So this is a 30 millisecond sample. You need 30 milliseconds to forward, same to backward, and then 1 millisecond to update your weights. So that was running somewhat live. And we get these power and energy. I couldn't do the precise comparison with GPU, but Tom just gave us some nice number on the event property on the Jetson Nano. So that was quite complementary to what we did here. Something I'm excited about this is doing these hybrid workflows, right? So a couple of things I did for this paper is something that is, let's say, pretty classical. You can train off-chip in PyTorch and then deploy it on-chip doing inference. Something that's a bit more unconventional, but that was actually practically interesting to me, was doing the training on-chip and then just pulling those weights and validating very quickly and getting, let's say, some test accuracy using the PyTorch package to not have to redo the test set on the chip as well, saving a little bit of time. And something I'm quite interested in, and I'm realizing now this is an old version of my slides, but something I'm interested in would be to do something a bit more advanced, something where you could do, for example, meta learning off chip, right? And if you imagine that you're going to encounter new data distribution when you're deploying on chip, you want your agent or whatever network to be able to adapt. So there's been some nice work by Emory showing that you can easily do MAML and then meta learning overall in spiking neural network. So this part could be done completely off chip, and then hopefully we can adapt effectively while deploying on chip. So an idea that I've briefly experimented with was to have the same union data set, but we've now some kind of rotations added to it. And you can imagine that maybe some rotation would be completely unseen, and we could try and see if this still works. Some conclusions, future works. Training on chip is possible, but scaling ever probably hard. And I think this came pretty clear with Tom's talk. The DRAM is now available on this on our Spinnaker 2 machines, so we can train probably bigger networks and data sets. I'd like to utilize NIR better to do better on to off-chip conversion. At the minute, this is all very handcrafted. I'm very excited to hear about this Jackson framework that we got a talk about yesterday, because fully event-based JAX plus NIR seems like a match made in heaven for MAML. So this should be pretty effective to try and do some meta-learning and adaptation. And overall, I think we should aim to try and get the best of both worlds, both off-chip and on-chip, via these hybrid workflows. Final thing, we've got this Spinnaker 2 tutorial on Friday, and I wanted to mention this will be probably the first time the user will be able to use live and run simulation on the actual Spin Cloud running at Dresden. So please come in and check us out. Thanks for your attention. Thanks for Timo and Bernhard for initiating this work at Telluride, and for all the colleagues at Spin Cloud for their help.